Jessy Lin, congratulations on your essay. Let's start off talking a little bit about human in the loop and how you came up with this idea and talk about some of your time at MIT and what you began to see in terms of the issues with the way that people were talking about machine translation.
Yeah, definitely. So first of all, like thank you, David, because this fellowship has been really great. I'm sure like everybody's kind of echoed that thought. But I kind of like came into this fellowship with a bunch of ideas related to stuff I'd done research on before, as well as like interests I have kind of like going into the future. So the idea of the essay really centers around kind of the beginnings of human computer interaction. So I kind of start off talking about some of the history, even like, way before the age of AI, when people were thinking about how do humans interact with computers, and how that idea has kind of evolved through history as we went from, these like giant mainframes that sat in like a whole room and had like many people operating it, to like personal computers and mobile devices and all these other things that we have today. And I started thinking about like, as we have all of these more interactive, or intelligent applications, how we can make those more interactive as well, using a lot of these same ideas. So I think like right now in artificial intelligence and machine learning, a lot of people are thinking about how do we make this more intelligent and more like powerful and more able to do like image recognition and speech recognition and like things like that, but not thinking as much about how to make it like interactive, thinking about like a human user at the end of it. So that was kind of the inspiration for the essay.
Yeah, one of the things that you talk about in the essay is this idea of human in the loop. And I'll let you explain it and I'll inevitably get something wrong, but I'll do my best to summarize it here. The example that I think a lot about is Tesla. So Tesla comes out with their self-driving cars. And when that happens, the computer is operating and that computer is driving the car. And so you're on the highway, you're on a road, and very famously, it is fairly easy for computers to do even 99.99% of what is required to drive a car. But this problem of self driving cars has been a lot more difficult because often computers will mischaracterize something that they're seeing and they'll see it as, say, a code, but it's actually a person and you cannot hit
Right.
the person. And so
Yeah.
what we've done is we've depended on computers to do the driving, but then to humans, for humans to be this backup layer that when something goes wrong, a human
Mhm.
stops texting, all of a sudden starts putting their attention on the road in front of them. But we found that this might not actually be the best way to do machine learning and self-driving cars. Why is that? What is wrong with this human in the loop model of trying to solve these complicated problems?
Yeah, definitely. So I would say like, a lot of people naturally think of the self-driving car example because like, the car drives and then like you kind of have this idea of like, okay, I can like take it over if something goes wrong. But like the fine details of how that handoff or that interaction happens, make a big difference, right? So I have this example in the essay where I think it was the American Bar Association that did some studies on, how this like what they call like semi-autonomous system works when the machine hands off control to the human. And there are details like how does the handoff happen? Like what kind of information is the human provided with? Like what context are they aware of? Is there an expectation that they're like attentive to the road, even though the car is like kind of operating autonomously? And all of these details make a difference as to like how successful the human is at like handling this like upcoming accident or like emergency situation. There's been a lot of thinking recently, especially because self-driving cars have been on the horizon for a while, but for some reason we just like can't get to full autonomy. So it's becoming like more and more of a like pressing issue that we need to think about. Like how can we have this like 90% accurate like machine learning autonomous driving system interact with a human in an effective way? Um, so I think there's some interesting research that's been going on this in this area of, like if we think about how the human like interprets the like actions of the system or like maintains some sort of understanding of what's going on, how the human plus machine driving system can be more safe and function more properly as a whole. Um,
So why don't you distinguish between human in the loop and human as backup? Because I think that I was explaining that as I was doing it, I was conflating the two. And so I want to make sure that we get that really clear before we move on to the rest of this
yeah,
essay and your proposals.
yeah. So human in the loop, as you might imagine, means like, okay, there's like some kind of autonomous system and there's a human operating somewhere in the loop. But the problem today is that like a lot of people have this very narrow vision of what that might look like, where the human in the loop operates as a backup for the machine. So the machine, is driving, and then like if something goes wrong, pass it off to the human. And you see this in a lot of other examples as well. So if you have like some kind of virtual assistant, like maybe like the like chatbot or like whatever machine learning like language processing algorithm you might have handles the requests that it knows how to handle and then hands off to some kind of human assistant when it doesn't know how to handle these examples.
Mm-hmm.
But kind of the idea that I kind of go on to talk about in the essay is there's a lot more like different ways for humans to interact with machines, like in a more tightly integrated loop, or in situations where like the human might initiate and call out to the machine when needed, and things like that. So yeah, lots of
So,
ideas too.
so why don't we talk about the two examples that you give? One is machine translation. So that is actually, you give the example of Douglas Hofstadter, who's a famous researcher who wrote Gödel Bach, and he shows what an original German paragraph looks like. Then he translates it himself, and then he shows the difference between his own translation and a computer translation to show some of the differences between them. So why don't we start there, and then we'll get into some of the computer human interaction that's happening at the cutting edge of chess.
Yeah, definitely. So in Douglas Hofstadter's example, he kind of goes through um, this German article and looks at like what are the weaknesses of Google Translate compared to human translators. So there are some like quotes from the article there, but basically he looks at like specific phrases and how Google Translate translates them compared to a native German speaker. And from everyday experiences with Google Translate, you can imagine like there are a lot of like fine, nuanced phrases or semantics that Google Translate doesn't quite capture, even though it does give you like the gist of what an article might be saying. And he breaks this down in very fine detail, looking at like, okay, when Google Translate translates this article, like what are the specific phrases that it misses, and how does this affect the overall translation as a whole, even after a human goes back and like corrects the translation that comes out of like Google Translate. And the difference that you see is like, because you're starting off with this very unnatural translation, even if you have a human, like what we call post-edit that translation, it looks like markedly different from what a human translator would produce. So the idea here is like, in a humans as backup human in loop situation, we might imagine like, oh, have a Google translate the sentence and then have a human go back and fix it. That's like the same as like a human, translating it from the beginning because like, you pass it through a human. But in reality, when you look at the example, you'll see like this actually produces like much lower quality than having a human initiate this loop.
Right. Yeah. Yeah. There's this great quote that you use in the essay from a translator who says something to the effect of, if I tried to translate something as backup, where the machine went first and I tried to just come in afterwards, that would just take me as long as just trying to translate it myself. And so
Right.
what you're saying is, because there are so many small little errors, but also you could think of the direction that the computer takes the translation on is fundamentally wrong. Actually trying to correct the entropy of the translation ends up often taking more time, or at least just as long time as just doing the translation yourself. So from there, why don't we get into chess and talk about, okay, so if that kind of backup post-edit translation where the computer does the work and then we come in after. That doesn't work. And that's sort of like, I'm almost thinking like a lawnmower. Like you come in and the lawnmower goes, and then you sort of sweep the grass to make sure that there was nothing missed. That's why I would
Yeah.
think of that. But you're trying to say something very different, which is actually this symbiosis in terms of thinking about how do humans begin to initiate the process of creation, and then how do computers come in afterwards. So let's talk about chess to get really concrete with what exactly you're talking about there.
Yeah. So there's this example from the history of chess. So this goes back to, you know, I think it was like the 1970s or 1980s when we were just beginning to come out with chess AIs. And actually, Garry Kasparov, who's like this great grandmaster, was recently defeated by IBM's chess AI. And he started thinking about like, okay, like what are some ways to reinvent the game of chess in the age of computers? And he came up with this idea of freestyle chess, which is what if we had humans playing chess using whatever kind of machine assistance or external resources they want. So he would have these games where like there were human players just like playing on their own. There would be like pure AI players, and then there would be like centaur players, which are humans using computers. And first of all, like the first thing that people saw at these matches was these hybrid human machine players consistently beat human players on their own and machine players on their own. So somehow, like even though the AI is like competing with a human, like the human contributes something that does better than just the machine on its own. And furthermore, like what he found was like at one of these tournaments, there was like a group of amateur players that were using like pretty basic computers, like normal hardware that they got from like their dad. And they're using like pretty normal chess engines as well, while like there are these grandmasters with like supercomputers and like the most advanced chess AI. And these amateurs were beating these grandmasters. And the reason was because they understood at some like deep level what each of their chess AIs and chess engines and computers, what their strengths and weaknesses were. So they were able to, take the output of one machine and say, this engine might be good at opening moves. So we're going to look at it for opening moves, and then we're going to use this engine for like the rest of the game and things like that. So using human judgment to kind of take bits and pieces of each of these, machine generated outputs and use it in a more integrated way. So I think like when I heard about this example, I think it was like one of the like best examples I've seen of the strengths of using human judgment in the loop with a machine. And since then chess AI has come a long way, but you can imagine that like in applications where what we need is even more open-ended, that human judgment can play even bigger and even more significant of a role.
Yeah, so what parameters does the person need in order to be better with AI? Like, if I competed against a deep blue IBM chess, it would probably be better for the AI to just go on their own because I'm not an expert in chess, and my decisions would probably hurt the algorithm's chance of success. But then if you bring in a chess master like Garry Kasparov, there is something that fundamentally different happens. And so, is my intuition correct in saying that the human needs to be of a sufficient level in order for things to work?
Yeah, I would say so. And I think that's like one of the interesting questions that I kind of explore in this essay, and it's still kind of an open question as well, which is like how, like what are we designing for here? Like who is the human end user? What do they know? And how do we design the machine to complement the human's abilities? So it does depend on like what the end user knows, right? Like if you're designing a tool for a domain expert versus like David who like has played a bit of chess but like maybe isn't like a grandmaster or something. And I think like that requires some understanding of the particular application and also like what the strengths and weaknesses of humans are in that particular case. So yeah, it's definitely like a
So do you see a parallel there between that and your return to the Tesla example that we spoke about at the beginning? Do you see an
yeah.
example there where what then, knowing what you know about chess, knowing what we've also discussed about machine translation and some of the errors with the post edit, which is sort of like a human as backup system, how then, if you were a product manager at Tesla, how would you be thinking about car design differently?
Yeah, yeah. So I think like there's this really great quote by Alan Kay, so one of the pioneers of human-computer interaction, where he says like understanding not just that end users have functioning minds, but that a better understanding of those minds would completely shift how we think about interaction. So this goes back to like, in this case of designing Tesla Autopilot, thinking about how humans respond in these kind of very like these situations that require very quick response, that require like split-second judgments, that require like taking stock of like your perceptual surroundings. Like understanding that can really shift how we think about designing autopilot. And even on the other side, like when we're designing autopilot, thinking about how other drivers on the road understand their surroundings as well. So like a lot of these emerging self-driving car approaches involve this field of research called like theory of mind, which is understanding how somebody else is like thinking about the situation. So, when, let me like contrast two approaches, for example. So if I'm like driving on the road and I see this other car kind of like shifting into my lane a bit, as a driver, like as a human driver, I understand what that means because I can imagine like, oh, if I were in that car situation, how would I kind of signal that I wanted to move into this lane? Well, I would like, like put on the signal and like maybe like start driving a little bit in that direction to signal that I'm like starting to move towards you. And like I would have an understanding of that because like I understand other people's goals and intentions. Like I have theory of mind. Whereas like in AI, what they see is like there's a car and it like has moved 5 pixels to the left. So a lot of these emerging self-driving car approaches are starting to think about like how can we use our understanding of human psychology to build more capable machines that interact in a human world. So a
Right.
lot
I
of
mean,
these,
even beyond that, like say that car moves 5 pixels to the left, it could be a couple different things. It could also mean that there is a hazard on the right side of the road and
right,
that car is trying to avoid something. So you could say, if the car is just trying to get into your lane very casually because they're trying to pass the car in front of them that might be 80 yards ahead of them, and it's a very casual thing, then you just want to slow down and maybe not even hit the brakes so that your red lights in the back come on because that will have downstream effects. Maybe you just want to ease off the gas. But there could be another scenario where that driver is coming into your lane because there might be a tire that is rolling across the street, and then you actually have to swerve left provided that there's no car behind you. Like then it gets really complicated. But the thing is, these are these edge cases, but that is when accidents happen.
yeah,
And this is why autopilot still isn't quite good enough for people to just take their hands off the wheel and let the car drive itself. But there's so many edge cases here.
yeah, yeah, definitely. So a lot of these little like ways that people signal to each other, like that counts as a sort of interaction as well.
Absolutely. Talk about Google Smart Reply. I really like this example that you gave in terms of what good interaction between humans and computers could be.
Yeah, yeah. So Google Smart Reply, for people who haven't seen it, is this feature in Gmail where you're like composing an email and then it kind of like auto completes your sentence based on similar sentences that you and other people have typed in the past, right? So this kind of style of interaction can be applied in a lot of different places. So the place that I talk about in this essay is translation. So if I'm a translator, again, like one way to interact with the machine is to edit the output that the machine has already generated. But another way is to take the translator's workflow, which is typing a translation, and just like level it up a little bit or like supercharge it a little bit with these Google Smart Reply style autocomplete translations.
Yep.
So the animation, I think, in the essay kind of illustrates it better, but like you can imagine as a translator, I'll be translating, and if it's a routine translation, the machine can just fill it in for me. I can like tab to autocomplete. If it's a different sort of more creative phrase, then what I can do is just continue typing. I don't need to, I don't need to deal with the machine's output. I can just like do what I normally do. So I think this kind of interaction is a bit more natural in that I, as the translator, or I, as the human, initiate the workflow and call out to the machine when I need to, and just do my thing when I don't.
Exactly, exactly. And the other thing is often I wonder if you'll be able to signal to the machine, like, I want you to complete this. So I'm thinking about, for example, one thing that drives me crazy is like when I do my drawings, like for my essays or put them on my website, I have to go specify how
Yeah.
straight I want the line.
Yeah.
And that is so manual that I want it to be like 100% straight, 89% straight. And then I always make little mistakes. I want it to be a little bit different. But what I would much rather have is for start drawing the line and for the machine, the app, to then give me a bunch of different options. And then I just click the straight line option and then it auto completes the straight line option. And then I have the straight line option, but say that I actually just want some edges and I want to make some nice sort of like S curves. Then I want to be able to, without even telling the computer, to have the computer realize that that's what I'm trying to do. But then once I
Yeah.
make like four of them, to then have the entire S curves auto complete. And I
Yeah.
could see this showing up everywhere where what a computer, what a human does is they get the path started and then the computer actually figures out what the rest of the pattern is. It's sort of like when you're in school, like even on SAT problems, they'll give you a pattern that's like, say that you're going 3, 6, 9, 12. The next one's going to be 15. But then very often, like if they're clever, what they'll do is they'll say it's 3, 6, 9, but then 12, and then the next one will be like 34, and they'll end up being some pattern that in retrospect is really obvious. But when you
Yeah.
were doing it, it didn't seem like the most logical one. And then you could just avoid the computer suggestion and go on to 34. And that's the kind of relationship that we want with computers that we don't have yet.
Yeah, yeah, definitely. And I think like a lot of these ideas merge really well with this emerging like tools for thought movement, where it's like, how can we build machines or tools that can help us think better? And I think
Shrinking
the
loops.
intersection here is like, well, with all these powerful new machine learning algorithms and like more intelligent tools, like we have a better sense of how to like help people do things like draw or write or manage information and things like that. So I think the possibilities there are pretty cool.
How much do you, as a researcher, worry about the idea that there is often knowledge in these artificial intelligence algorithms that we don't actually know about? So you gave the example of in one hospital, the diagnoses were different from the other ones, but then there were certain reasons from that. Talk about that example because that's what concerns me. There's like this intellectual dark matter embedded within the knowledge, and we actually can create the systems, but we can't actually piece out all the knowledge that is coming together in order for those systems to work.
Yeah, definitely. So this is like a super kind of ripe area of research. So I would refer people to like interpretability, explainability, and research on like fairness in machine learning, which looks at um, basically like how can we open up the black box of machine learning? How can we like make the outputs or like the reasons that a machine outputted a particular thing comprehensible to humans? So this is applicable in like you mentioned, like medical diagnosis, where if we make a diagnosis, we want to understand like what the factors are that contributed to that diagnosis. One, to make sure like, okay, like as a doctor, I want to make sure just a sanity check, the machine is actually using predictive variables that are relevant for this particular patient. So, like in the example that I talk about in the essay, um, there are some machine learning algorithms like that might be trained on biased data sets where like all the patients from one hospital um, have the disease and all the patients from another hospital don't. Maybe like one hospital is for more severe cases and therefore like there's this inherent bias in the data. And because like we're not imposing any sort of like domain knowledge, like the choice of hospital doesn't matter for a particular diagnosis. This happens just to be like a spurious correlation. The machine is picking up on these correlations and using them to predict like incorrect outcomes. So I would say like, yeah, like people are thinking about this a lot, about how to make machines like more fair, more um, like unbiased, but it's definitely something that is still an open problem. And I think a lot of the reason why interaction might be like a really good approach to kind of manage these risks. Because if I'm interacting with the machine, like, or if I'm initiating the workflow, I can kind of like manage how the machine fits into the larger context. So I can like use it in very specific situations where I know like, okay, I just want to understand like, this, like what the machine thinks about this particular thing. And like, I'm still kind of like, as a doctor managing like all the other information about the patient, I'm not just like relying entirely on the machine to diagnose like without like doctor oversight or something. Um, so yeah.
So I'm going to throw out a narrative, and you tell me where it's right and where it's wrong. So there's a big narrative that has swept across the AI landscape from what I've observed, which is if you have more data, you will automatically win because more data creates this compounding exponential effect, and you end up with these small advantages. But then, because of the nature of compounding, those small advantages get bigger and bigger and bigger over time, and you end up having such a data advantage that nobody can compete with you. True or false?
Yeah, I think this is a really hot question as well. Like, I think we've been surprised by how effective data is. Like, a lot of the things we didn't think we could do just because we collected bigger data sets and built bigger models. Like a lot of, let's say, like speech recognition or language understanding seems to come about when we have just like, 100 plus GPUs thrown at the problem. Um, but I would say like a lot of the things that people are seeing in industry is like one, this is very expensive and not sustainable as a strategy, and two, we're not even sure like whether we can get to human level understanding just by throwing more data at the problem. So like self-driving cars is the most obvious example where we just like we've thrown so many resources, not only like computer resources but like human resources at the problem, and we still haven't gotten to the point of full autonomy. So like the question is like, are we willing to take the risk, or you know, do we want to kind of like think about the possibility that it's not an exponential curve, but like a curve that flattens out over time? And what we need maybe at some point is like another research breakthrough before we can really get to full autonomy or language understanding or like human level reasoning.
Do you have a sense of why, with, say, Google Translate, why that has gotten so good? Like, the big one for me is like when I go, okay, Google, and I type into it and I say, just had a really good conversation with Jesse. It's a beautiful Sunday in San Francisco, and
Yeah.
now I'm going to go on a walk with my mom. If I type that into Google, it's so much better than doing that into Siri. So is that a data thing? Is that like a way of actually the way that the Google algorithms work that are better? Maybe Apple's really bad. Like, what's actually going on there?
Yeah, I would say in that case, it's like a combination of like the data and the particular like model that Siri might be using versus Google. I think in other cases, like, a big problem that startups have is like a purely data problem. So like even though they might have like PhD students on like the founding team, as a startup, you just can't compete with like the same sources of data that Google has for a lot of these applications. So yeah, definitely like a combination of both
Wait,
in a
that's
lot of.
really interesting. So then what are the solutions there? Like, could you start a company that's just like, hey, we have a ton of data and that's all that we do. We just open source data, we clean it up. So
Yeah.
let's talk about a solution for that.
As for the data problem and like how it applies to startups, yes, that is a big problem that startups face. And I think a lot of the reason why people turn to humans in the loop, which is like, as a startup that wants to incorporate some machine learning technology, I need some data to like bootstrap this process. How do I get that data? Either I use open source data sets, which is thankfully like in the machine learning community pretty common. Like for a lot of these papers that are published, they also like release a data set to help the community kind of work on the same problem. But if I'm working on a sort of proprietary problem, like I want to label product images and like I need to train on specific products, I might incorporate a human in the loop to label data while I'm building up my model. So like this is like the whole kind of, I guess, like playbook strategy for machine learning startups nowadays, which is to start the flywheel of having a machine learning algorithm and then having this like human as backup to label the examples that are hard. But the argument that I'm kind of presenting in this essay is thinking more about like, as a startup, you can do that. You can have a human as backup to label these hard examples, but you can also start with a human first strategy and still collect the data you need to, gain the advantage and like build a better model and so on by thinking about how you can integrate better with humans from the beginning.
How much, like I have a friend who runs a hedge or a big investment firm, and it's a quant firm. And one of the most surprising things that I've learned from him is inordinate amount of the company resources just goes into cleaning up the data. That the data that they actually get, even though they're buying the data, even though it's really high quality, even though it's from great sources and it's advertised as good, clean data, even then they have to continue to clean it up. How would you weigh the difference in priority? And I'm sure there's a context dependent element here, but how would you weigh the difference in priority between cleaning up data and then just trying to get more data?
Mm, that's a good question. I would say like both are pretty important. Um, having clean data is important because like, if you have, there's a phrase called like garbage in, garbage out, right? So
Right.
if you have data and you train your model on it, you're going to have bad results. But then at a certain point, like you also need a like critical mass of, or you need like a lot of data to train these algorithms in the first place. But like the problem is like, you need both. You need high quality and lots of it. So that's kind of the problem that people face.
And last question, what do you think the binding constraint is on acquiring data? So is it that we don't have enough sensors? Is it a privacy issue that doesn't allow us to collect data? Is it a sharing issue that a lot of the data is locked into the walled gardens of Facebook and Google and Apple? What is actually preventing more data from being captured? Like you could even take something like a Stephen Wolfram Alpha, where in Wolfram Alpha, the language, it allows us to look at real world data that we wouldn't have in other systems. And so it's like making new parts of the world legible. So what is the binding constraint on us not having 10 times more data, which would allow us to have more food to give our training sets?
Yeah, I mean, I would say just like getting high quality labeled data sets in general requires a lot of labor. Um, so like if I want to, let's say, train a machine to answer questions, I need to have like a high quality data set of questions and answers. And who's going to produce the answers? Like human labor. And a lot of that times that labor can be very expensive. Like if you're, like a medical application, for example, you need doctors to like label these examples. You can't just have some, like low cost worker in another country doing that. So really, I think like for every application, you need like a very high quality tailored data set for that application. And that's a lot of what the bottleneck is for a lot of these startups and companies.
Jessy Lin, congratulations on your essay.
Thank you, David. Thank you so much for the fellowship.